When a standard internal combustion engine throws a rod or blows a gasket, the diagnosis is usually just a matter of physical forensics.
Right, yeah. You pull the oil pan and just look inside.
Exactly. You find chunks of metal, you point to the fractured steel, and the story basically writes itself. It's a catastrophic binary mechanical failure.
It's very tangible. The autopsy of a combustion engine is, the damage is macro level. It's undeniable and it's localized.
But the architecture of a high-voltage electric vehicle battery requires a complete paradigm shift in how we think about wear and tear.
Oh, absolutely. It's a whole different world.
We are no longer dealing with a static fuel tank or like a mechanical pump. We are dealing with a highly volatile, living electrochemical organism.
I like that word organism,
Yeah.
because it really is.
Yeah, and it experiences chronic stress, thermal fatigue, and just this unavoidable systemic decline that doesn't exactly leave chunks of metal on the highway.
Which creates a really fascinating challenge for the diagnostic software. I mean, we're asking a computer to run a continuous, real-time physiological assessment of a chemical system.
Right.
A system that is constantly degrading at the atomic level, mind you.
And that brings us to the core focus of today's deep dive. We are unpacking the technical architecture behind the ultimate diagnostic fault codes for high-voltage battery degradation.
Good big ones.
Yeah, specifically the industry standards, P0A7, which represents battery pack degradation, and BMS067, indicating capacity fade reached limit.
And those codes are serious. They represent the terminal stage of an EV battery's life cycle.
This isn't a glitch.
No, not at all. This is an irreversible, pack-level physical and electrochemical aging event.
Okay.
When a battery management system, or the BMS, throws a P0A7 fault, it is fundamentally different from, like, a sensor glitch or a software bug.
You can't just reboot it.
Exactly. There's no patch, there's no calibration, and no reset procedure that can reverse it. The system has mathematically and physically verified that the battery can no longer safely store or output its rated energy.
So our objective today is to trace the complete life cycle of this failure. For you listening, we're going to explore the 5 dimensions of this specific fault's functional safety strategy.
It's a massive journey.
It really is. We'll start at the microscopic root cause of the electrochemical decay, then move to the software architecture the BMS uses to actually diagnose it.
And then we have to look at the massive preventative measures engineers build into the design phase, the DFMEA.
Right, and from there, we'll hit the factory floor to see the PFMEA manufacturing controls.
Don't forget the physical validation.
Oh, for sure. Finally, we'll look at the brutal DVP&R physical validation tests these systems just have to survive before mass production.
The sheer depth of the engineering required just to monitor this decay, let alone delay it, is staggering. I mean, the functional safety strategies surrounding P0A7F are arguably some of the most complex algorithms operating in a consumer vehicle today.
Well, let's start with the microscopic anatomy of the aging process, the root cause analysis.
The seat of the crime, basically.
Exactly. To understand the diagnostic triggers, we really have to look at what is actively destroying the battery's capacity over thousands of charge cycles.
So the source material categorizes this into a few primary mechanisms. The first being loss of lithium inventory.
Or LLI.
Right, LLI. Now, in a lithium-ion cell, the electrolyte reacts thermodynamically with the graphite anode during operation.
And this forms a layer, right?
Yeah, it forms the solid electrolyte interface layer, the SEI layer.
Now, this SEI layer, it's not a malfunction. It's actually a critical, necessary passivation film, right? Like, without it, the electrolyte would continuously decompose on the surface of the anode, and the battery would just fail almost immediately.
Spot on. But the problem is that the SEI layer is not perfectly stable over the long term.
Right, because of the heat and the charging.
Exactly. Under high thermal loads in deep charge cycling, the graphite anode physically expands and contracts.
It's literally breathing.
Yeah, this mechanical breathing causes that protective SEI layer to crack.
And when it cracks, fresh graphite is exposed to the electrolyte, which forces the chemical reaction to occur all over again just to heal that microscopic fracture.
It's like a scab forming over and over.
Yeah. But the fundamental problem here is that this healing process consumes active lithium ions. It permanently binds them into the structural matrix of the new SEI scar tissue.
They're trapped.
Completely. They are permanently removed from the usable electrochemical pool.
And the cascading effect of that is severe. Because the SEI layer is continuously thickening to heal these microfractures, the internal ohmic resistance of the cell climbs.
Because the electrons have a harder time getting through that thick scar tissue.
Exactly. And the loss of active lithium means you simply have fewer charge carriers available to shuttle back and forth between the cathode and the anode. The capacity fade curve accelerates as that layer degrades.
So while the lithium inventory is being depleted at the anode, we also have catastrophic structural issues occurring at the cathode, particularly with modern high-nickel chemistries.
Right, which brings us to the second root cause, loss of active material. LAM, yeah. These high-nickel transition metal oxides, they're engineered for really high energy density, but they are incredibly sensitive to lattice strain.
Especially when subjected to massive electrical currents, right? High C rates and high temperatures.
Oh, the electrochemistry inside a high-nickel cathode during a high C-rate discharge is violently stressful.
I can imagine.
As massive amounts of lithium ions are rapidly extracted from the cathode's crystal lattice, the structure undergoes severe volume changes and anisotropic contraction.
Just warping under the stress.
Over time, this repeated mechanical strain causes transition metal dissolution.
The crystal lattice literally fractures, like we see severe microcracking all across the cathode particles.
And those microcracks physically isolate entire sections of the active material from the carbon conductive network.
So even if you have surviving lithium ions ready to, intercalate and do their job, the pathway is severed.
The road is out. The physical capacity limit of the battery, the true Cmax parameter, it permanently shrinks because the material required to house the energy is structurally destroyed.
So we have a two-front molecular war going on here. The SEI layer is trapping our charge carriers on one side, and the cathode lattice is collapsing and destroying the storage infrastructure on the other.
It's grim.
It is. But the diagnostic criteria for P0A7F also hinges on how these microscopic failures scale up to ruin a massive multi-module battery pack.
This introduces the macro-level issue of the thermal cascade.
I really like conceptualizing this using the wooden barrel effect.
Oh, right, the stave analogy.
Yeah. If you have a wooden barrel made of 100 staves, the maximum volume of water it can hold is dictated entirely by the single shortest stave.
Which perfectly applies to a high-voltage architecture.
Yeah.
Your battery pack is limited by its weakest, most degraded individual cell.
Because they're all linked.
Right. In an ideal world, all 2,000 cells in a pack would age at the exact same rate. But in reality, manufacturing variances in the cooling architecture create minute thermal gradients.
For instance, if the thermal interface material, the tin paste that connected the cell bottom to the liquid cooling plate, if that has just a millimeter-sized void or an air bubble, the thermal conductivity in that localized spot plummets.
And that localized cooling failure means that specific cell might operate just 3 to 5 degrees Celsius hotter than the surrounding cells.
And 5 degrees seems negligible, but the Arrhenius equation dictates that the rate of chemical reactions scales exponentially with temperature.
Including the parasitic reactions causing SEI thickening and lattice collapse.
Heat is the ultimate catalyst here. That single cell with the tiny TIM void undergoes rapid, localized loss of lithium inventory and loss of active material.
Its direct current internal resistance, or DCIR, just spikes aggressively compared to its neighbors.
Because the cells are wired in series, right? So this high-resistance hotspot becomes a massive bottleneck.
Huge bottleneck. During heavy acceleration, that elevated internal resistance causes a severe voltage drop across that specific cell.
And the BMS sees that.
Yeah, the BMS detects this localized voltage sag and is forced to throttle the output power of the entire pack.
Just to protect the one weak link.
Exactly, to prevent driving that weak cell into a catastrophic undervoltage state. The entire system's performance is dragged down by one exponentially aged cell.
Which transitions us perfectly into the second dimension of the safety strategy, the tech architecture and the BMS diagnostic logic.
Right.
We've established the physical decay, but the true engineering marvel is how the BMS actually accurately measures this decay in real time.
Because it can't crack the casing and put the cells under an electron microscope.
No, it has to rely entirely on software state estimation. And the primary hurdle here is signal noise, which the designers solve using a dual timescale observer architecture.
State estimation is inherently noisy because of how EVs are driven. I mean, the BMS has to simultaneously calculate the state of charge, the SOC, which dictates your remaining driving range,
right,
and the state of health, the SOH, which tracks that permanent degradation we've been discussing.
And the dual timescale observer computationally decouples these two metrics because the SOC is highly dynamic, right? It's a
I mean,
fast variable.
very fast. Every time a driver floors the accelerator or hits the regenerative brakes, there are massive current spikes.
So if the BMS attempted to calculate the long-term state of health, which is a slow variable during these high current events, the data would just be corrupted by massive ohmic polarization.
The rapid change in current, multiplied by the internal resistance, creates temporary voltage distortions. The state-space equations would self-excite, the Kalman filters would diverge, and the SOH estimation would be completely useless.
Be like trying to take your resting heart rate while sprinting on a treadmill.
That's a perfect analogy. By isolating the slow variables, the BMS ensures that the long-term degradation math is only processed during stable, low-current resting states.
Yeah.
It filters out all the chaos of highway driving.
But even with that filtering, tracking the true maximum capacity, the Cmax, over years of ownership is notoriously difficult because of ampere-hour drift.
Right, because traditional Coulomb counting is fundamentally flawed.
That's where the BMS simply integrates the current over time to track electrons moving in and out, right?
Yeah, like counting people walking through a turnstile.
Yeah.
But no current sensor has zero offset error.
Right.
A current sensor might have a 0.1% accuracy tolerance. Over a single charge, that error is absolutely meaningless.
But EV owners rarely do full 0 to 100% deep cycles.
Exactly. They commute, they plug in at 40%, they unplug at 80%. These constant shallow microcycles cause that tiny sensor offset error to compound mathematically over months.
The turnstile loses count. The BMS might calculate the pack has, say, 65 kilowatt hours of usable capacity based on integrated current, but due to drift and the physical LLI decay, the true physical capacity might only be 58 kilowatt hours.
And to correct this, without forcing the driver to, purposely drain their battery to zero on the side of the road, the BMS deploys a brilliant diagnostic algorithm.
Incremental Capacity Analysis, or IC.
Yes, ICA relies on high-frequency differential calculus, specifically analyzing the dQ/dV curve.
That's the derivative of capacity with respect to voltage.
Right. During a slow, stable AC charging session, the voltage of a lithium-ion cell does not increase in a perfectly straight line. The graphite anode undergoes distinct staging phase transitions as lithium intercalates into the layers.
And these phase transitions create subtle plateaus in the charging curve, right? Where the battery absorbs a significant amount of charge capacity, the DQ with almost zero change in voltage, the DV.
Exactly. By taking the derivative of that charging curve, the ICA algorithm transforms those flat electrochemical plateaus into sharp, highly visible peaks on a mathematical graph.
That's so clever.
It is. The magnitude, the area, and the specific voltage locations of these peaks act as a distinct chemical fingerprint of the active material currently available in the cell.
It's essentially performing a non-invasive MRI on the electrochemistry while you charge in your garage.
Exactly. By comparing the height and shift of these dQ/dV peaks against the factory baseline, the BMS can calculate the exact extent of the lattice collapse and lithium inventory loss.
It totally bypasses the accumulated error of the current sensors. It mathematically reestablishes the true Cmax and burns that updated truth into the non-volatile EEPROM memory.
The EEPROM integration is crucial. Electrically erasable programmable read-only memory ensures that even if the 12-volt accessory battery dies and the BMS loses primary power, that precise historical degradation data is never lost.
The long-term health timeline remains intact.
Oh,
And when that dQ/dV calculus determines that the capacity fade has finally crossed the critical threshold, triggering the P0A7F fault, the BMS initiates FNEA MSR dynamic derating.
the hammer comes down.
Yeah. The system rigidly enforces a map that permanently bans the vehicle from accepting DC fast charging. It completely disables the high-voltage contactors if a supercharger is plugged in.
It seems like a harsh restriction. I mean, you're essentially crippling the car's road trip viability.
But the physics of a degraded cell leave the BMS with no alternative, right?
None. The restriction is a direct response to the heightened risk of thermal runaway. As a high-nickel cell suffers from severe loss of active material, its thermal stability window just collapses.
The thermal runaway trigger temperature, the point where the exothermic reactions become self-sustaining, drops significantly in a highly degraded cell.
Right, so pushing 250 kilowatts of DC fast-charging current into a depleted, structurally damaged anode is just a recipe for lithium plating.
Because the lattice has collapsed, so the intercalation sites where lithium ions normally park inside the graphite are just gone.
With nowhere to intercalate, The metallic lithium ions pile up on the surface of the anode and reduce into solid metallic lithium. And if high current continues to flow, this surface plating forms microscopic, needle-like crystalline structures called dendrites.
And these dendrites grow directionally toward the cathode, right? And they possess enough mechanical rigidity to physically pierce the polyethylene separator, isolating the two electrodes.
Yes, and a pierced separator results in an instantaneous, hard internal short circuit.
Which is terrifying. The ensuing massive current discharge localized at the puncture site generates catastrophic heat, immediately pushing that degraded cell past its lowered thermal runaway threshold.
Which is exactly why the BMS permanently locks out fast charging, because the calculus proves the structural integrity required to safely absorb that current no longer exists.
It is a non-negotiable functional safety mandate. That harsh reality brings us to the third dimension, the design failure mode and effects analysis, or DFMEA.
The design phase.
Right. Knowing that deep structural degradation inevitably leads to a severity 8 risk like lithium plating and thermal runaway, design engineers must build massive preventative buffers directly into the physical hardware and software architecture long before mass production.
In DFMEA automotive standards, a severity 8 dictates a high action priority. The mitigation strategies have to be absolute.
And the most prominent physical mitigation strategy dictated by the DFMEA is the rigid optimization of the NP ratio, right? The negative to positive capacity ratio.
Exactly.
I was looking at the specifications for this, and the design standard mandates an NT ratio strictly greater than or equal to 1.12.
Which is a huge deal.
Yeah, you are mathematically forcing the physical design of the anode, the negative side, to have at least 12% more total storage capacity than the maximum lithium inventory provided by the cathode. You are intentionally building dead weight and excess volume into millions of battery cells strictly as a safety margin.
It is a massive concession in terms of volumetric energy density and raw material cost. But it is fundamentally required to combat lithium plating.
Like we just discussed, cold temperatures or fast charging rates cause lithium to back up at the anode surface because the intercalation kinetics slow down.
Think of it like a parking lot. By oversizing the anode by 12%, you are vastly increasing the total surface area and the sheer number of parking spaces available.
So even when the chemical kinetics are sluggish and ions are backing up like cars at a toll booth, the massive surplus of spaces ensures the lithium always has a structural void to drop into.
Right, which prevents surface reduction and dendrite formation. The 1.12 ratio guarantees that over a projected 10-year lifespan, even as the SEI layer thickens and consumes space, the anode maintains enough buffer volume to accept fast-charging currents without initiating plating.
It is a raw, physical margin of error woven directly into the chemistry.
But physical design isn't enough. Alongside the physical NP ratio, the DFMEA also mandates a highly advanced software mitigation strategy.
Right. The BMS must run a continuous stress tracking algorithm called the rainflow counting model. And I found this fascinating because rainflow counting is actually an aerospace engineering protocol.
Oh, really?
Yeah, it was developed by Tatsuo Endo to track cumulative metal fatigue in aircraft structures. When an airplane wing hits turbulence, the stress isn't constant, right? It's a chaotic series of microfluctuations.
Endo's mathematical model takes a completely chaotic, noisy graph of structural stress peaks and valleys and systematically breaks them down into closed-loop cycles.
Right, measuring the exact amplitude and mean stress of every microscopic impact. It translates noise into a quantifiable cumulative fatigue index.
And automotive software engineers adopted this exact aerospace model and applied it to battery electrochemistry.
Because driving an EV is functionally identical to a wing hitting turbulence. You have a constant chaotic fluctuation of thermal spikes, C-rate discharge pulses, and mechanical expansion stress during every single commute.
So the BMS uses a Markov matrix to log these varying amplitudes of stress without overwhelming the limited computational memory of the controller.
It's actively tracking how deep every discharge is, how high the thermal delta was during the cycle, and logs it into a cumulative structural fatigue score.
And then the BMS uses this rainflow fatigue score to dynamically restrict the state of power, or SOP.
Rather than waiting for the DQDV algorithm to detect a massive loss of active material years down the line, the BMS actively throttles the maximum power output based on real-time cumulative fatigue.
It's proactive. If the rainflow algorithm determines the battery has endured a high concentration of severe high-temperature microcycles, it subtly reduces the maximum current limits to protect the crystal lattice from further collapse.
It constantly adjusts the performance envelope based on the historical trauma the pack has absorbed.
The integration of aerospace fatigue modeling into consumer automotive software is just a testament to how seriously the DFMEA views electrochemical degradation.
However, all the intricate aerospace math and perfect 1.12 NP ratios are entirely useless if the physical cells are manufactured poorly.
Very true.
Which moves us to the fourth dimension of the safety strategy: process failure mode and effects analysis, or PFMEA, the factory floor.
Where theoretical physics meets heavy industrial execution.
And the tolerances are absurdly unforgiving. The first critical control characteristic, or KCC, on the production line targets that 1.12 NP ratio buffer using continuous beta ray scanning.
So when manufacturing electrodes, machines coat massive, miles-long foils of copper and aluminum with wet chemical slurries containing the graphite or high-nickel active materials.
And the thickness and surface density of that coating dictate the localized capacity of the cell.
Right, so if the coating machine stutters, even slightly, and lays down a patch of anode slurry that is a fraction of a micron too thin.
That specific localized area on the foil will have an NP ratio that drops below 1.0.
Exactly, which means in that microscopic localized zone, there are fewer intercalation sites than arriving lithium ions.
It creates a localized lithium plating risk that the overall cell design cannot protect against.
To prevent this, the PFMEA mandates 100% online continuous beta ray scanning.
Which is wild. The factory literally shoots nuclear radiation beta particles through the wet electrode foil as it passes down the production line at high speeds.
The sensors measure the exact absorption rate of the beta radiation passing through the material. Because the absorption is directly proportional to the mass and density of the coating, the system can calculate the surface density of the active material down to the microgram in real time.
So if the density deviates by even a fraction of a percent, the system feeds a closed-loop signal back to the coating die, adjusting the slurry flow pressure in milliseconds.
It virtually eliminates the possibility of localized NP imbalances.
Moving down the line, the PFMEA also strictly regulates electrolyte injection and cell sealing pressure.
Oh, this is a huge one.
The source material defines this as a critical KCC because of the massive risk of long-term microleaks. The electrolyte solvent is highly volatile, right?
Very. If the pneumatic sealing pressure of the cell casing is off by a tiny margin, the seal will hold initially, sure, but over years of thermal expansion, microscopic pathways will form.
And that volatile electrolyte will just slowly evaporate through those microleaks.
And as the cell dries out, the ohmic resistance skyrockets because the lithium ions lose their transport medium.
This leads to a severe, nonlinear collapse in capacity that perfectly mimics accelerated P0A7F degradation.
Right. So statistical process control (SPC) is heavily enforced on the injection volume and pneumatic sealing tools to ensure a perfect hermetic seal across millions of units.
But the structural assembly of the modules is where the PFMEA encounters one of its most delicate balancing acts: module pre-stress.
The clamping.
Yeah. To build a robust battery pack capable of surviving road vibrations, the factory uses massive hydraulic presses to clamp dozens of cells together between heavy steel end plates. And intuition suggests you should clamp them as tightly as possible to create a rigid, vibration-proof brick.
Right. But the manufacturing specifications strictly limit the maximum hydraulic force. Overclamping is heavily penalized.
It goes back to the physical breathing of the cells we mentioned earlier. When lithium ions intercalate into the graphite layers of the anode during charging, the anode's physical volume actually expands.
A cell fully charged to 100% SOC is measurably thicker than a cell at 0% SOC.
The battery has to physically swell. If the factory clamps the module with excessive dual closed-loop hydraulic pressure, the cells are trapped in a vise.
So when the customer charges the car, the graphite tries to expand, but those steel end plates provide thousands of pounds of counter-resistance.
And that inward compressive force has to go somewhere. It transfers directly into the internal architecture of the cell.
The immense mechanical pressure effectively crushes the delicate transition metal lattice of the cathode.
It induces severe localized loss of active material simply through brute mechanical force.
Which is why the PFMEA controls require the hydraulic presses to hit an impossibly tight parameter, applying enough torque to prevent resonant vibration damage, but leaving exactly enough expansion tolerance to allow the cells to breathe over a decade of cycling.
The level of precision required across all these 5M1E variables, man, machine, material, method, measurement, and environment, is captured in the final factory step: MES barcode binding and end-of-line testing.
Every single cell undergoes a preliminary formation charge.
Right, the factory measures its exact initial Cmax capacity and its AC internal resistance, binds that data to a laser-etched 2D barcode, and uploads it to the manufacturing execution system.
And that specific cell's DNA is then physically flashed into the EEPROM of the BMS that will eventually manage it.
The brain knows the exact baseline resistance of its pack before the vehicle ever rolls off the line.
And the factory validates the entire assembled pack using a strict statistical capability index, or CPK. The requirement is a CPK greater than or equal to 1.67.
In Six Sigma manufacturing, a CPAC of 1.33 is the standard for high-quality control. So demanding a 1.67 means the variance in internal resistance across the thousands of cells in the pack is statistically microscopic.
It is the ultimate defense against the wooden barrel effect. They are mathematically guaranteeing that they haven't accidentally installed a short stave.
But even with a CPAC of 1.67, automotive engineering dictates that theoretical perfection must be physically proven.
Which brings us to the fifth and final dimension of the functional safety strategy, the DVP&R, or Design Verification Plan and Report.
This is the validation phase where engineers purposefully subject the perfect hardware and software to extreme combined stress torture tests to ensure the fail-safes operate flawlessly under worst-case scenarios.
It's brutal.
Let's break down the 4 core DVP&R tests mandated for the P0A7F diagnostic system. The first is the WLTC Dynamic Conditions ICA Learning Test. This is explicitly designed to validate that DQ-DV differential calculus algorithm we covered earlier.
Because validating advanced math requires feeding it heavily corrupted data to see if it can still extract the truth.
Right. So the engineers take a physical validation battery pack and artificially age it on a bench simulator for over 800 deep charge cycles, driving its true physical capacity down to roughly 72%.
It is severely degraded, suffering from massive LLI and LAM.
Then they place this heavily degraded pack into an environmental testing chamber and swing the temperatures wildly, dropping it to -10 degrees Celsius, bringing it to 25 degrees, and then baking it at 45 degrees.
And crucially, they do not allow the BMS to see a full charge curve. They subject the pack to continuous frustrating shallow cycles, only charging between 30% and 70% SOC.
They are actively trying to induce severe drift. They are starving the current sensors of a 0-point calibration, applying extreme thermal noise, and using a structurally degraded battery.
And under these chaotic conditions, the BMS must run its ICA-DQ-DV calculus and accurately calculate the true remaining capacity of the battery.
The DVP&R standard dictates the software must lock onto the true Cmax with an error margin of no more than plus or minus 3.0%.
It must find those electrochemical plateaus through the noise of the cold, the shallow charging, and the internal resistance spikes.
If the calculation diverges or exceeds the 3% tolerance, the software fails validation and cannot be deployed to mass production.
The second test validates the structural integrity against the clamping forces we discussed, the pre-stress and thermal fatigue test.
Right. This one requires building 2 distinct testing modules. Module A is the control, assembled perfectly to the specified hydraulic torque tolerances. Module B is deliberately botched. The factory overloads the clamping force by 150%, actively crushing the cells.
Both modules are then placed on a multi-axis vibration rig to simulate continuous 3D road vibration and simultaneously locked into a thermal shock chamber.
They slam the temperature from -40 degrees Celsius straight to 85 degrees Celsius, inducing massive, violent thermal expansion and contraction.
And they run this torture cycle 1,000 continuous times.
Following the 1,000 cycles, the physical validation requires a teardown. Engineers physically slice the individual cells open and examine the cross-sections under a scanning electron microscope, and SEM.
They are looking directly at the molecular bricks and mortar of the cathode.
For Module A, the perfectly clamped module, the SEM must reveal an intact crystal structure with no macroscopic peeling of the active material from the current collector. Its internal resistance must still fall within the acceptable design baseline.
In Module B, the overclamp unit will predictably show catastrophic lattice collapse and severe microcracking under the SEM.
The primary purpose of Module B is actually to validate the factory's end-of-line testing parameters, proving that the resulting resistance spike from the crushed lattice is severe enough that the factory SUPI quality checks would easily catch it and reject it before it ever reached a vehicle.
So the hardware survives the shock. But what happens if a cell fundamentally fails while the car is in motion?
This leads to the most critical functional safety validation, the FTTI Highway Limp Mode test. FTTI stands for Fault Tolerant Time Interval.
Let's visualize the testing environment. The simulator has the vehicle's powertrain operating in a ready-run state, mimicking highway driving at 70 miles per hour under high torque demand.
While the system is pushing massive power, the test engineers manually inject a critical fault via the software console. They instantly drop the simulated SOH capacity to 68%.
They are simulating an instantaneous catastrophic exhaustion of active material.
The car is basically having a heart attack at 70 miles per hour. The moment the software injects the fault, the clock starts. The BMS has exactly 10 to 15 seconds of debounce time.
This debounce window is a critical software filter. The BMS spends these 15 seconds running rapid diagnostic checks to verify that the sudden drop isn't just a loose sensor wire or transient electromagnetic interference.
Right. If the BMS confirms the mathematical reality of the fault over that 15-second debounce window, it permanently writes the P0A7F fault flag into the EEPROM memory.
This is a hard code. A dealership technician cannot simply clear it with a scan tool.
But the vehicle is still traveling at 70 miles per hour. This is where the strict FTTI window activates. From the exact millisecond the fault is confirmed, the BMS has exactly 2.0 seconds to coordinate with the vehicle control unit, the VCU, to execute a life-saving intervention.
Within those 2 seconds, the VCU must pull back the motor torque and forcibly limit the maximum discharge power of the battery to between 30% and 50% of its normal output.
It forces the powertrain into level 3 heavy limp mode.
The complexity here is the requirement for a smooth torque transition. If the VCUs simply sever the high-voltage contactors in 2 seconds, the vehicle would suffer a massive loss of kinetic energy, resulting in severe torque jerk.
The sudden deceleration could cause the driver to lose traction and crash at highway speeds.
The algorithm must perfectly feather the torque reduction, safely slowing the heart rate of the powertrain without destabilizing the chassis dynamics.
Concurrently, the software immediately disables pure EV driving modes if it's a hybrid, forces the internal combustion engine to take over the load, and permanently locks the maximum state of charge limit to 50% to prevent any possibility of future overvoltage thermal runaway.
It guarantees the vehicle limps to the dealership safely without initiating a fire.
And that limp to the dealership introduces the final DVP&R software validation hurdle, after-sales UDS calibration.
Right. When the customer arrives at the service center and a technician physically unbolts the degraded, highly resistant battery pack and installs a brand new $15,000 replacement pack, the diagnostic software faces a critical mismatch.
Because the BMS logic has spent years accumulating data on the old pack, its rainflow fatigue matrices, its DQ/DV degradation curves, and its heavily restricted dynamic derating maps are all actively running in the processor.
So if the car boots up with a new battery, the BMS will look at the pristine hardware but apply the old, heavily restricted mathematical models.
The vehicle will instantly trigger false under-voltage faults, cripple the new pack's range, and ruin the hardware.
To prevent this, engineers utilize the Unified Diagnostic Services Protocol, or UDS. This is the standardized ISO 14229 communication protocol used by all automotive diagnostic tools.
The DVP&R test validates the strictness and speed of the service bay reset procedure. When the technician sends the specific UDS command to reset the battery history, the BMS is required to completely erase years of historical aging coefficients from the EEPROM in less than 500 milliseconds.
It wipes the slate clean, resetting the capacity algorithms back to the beginning of life, or BOL, factory baseline.
But the software validation isn't over. A wiped memory isn't enough. The BMS must prove it can accurately map the new hardware. The test requires the technician to perform one complete deep cycle on the new pack.
They discharge the new battery down below 10% SOC and then plug it in for a slow AC charge until the tail current drops to near absolute zero.
And then, crucially, they let the vehicle rest undisturbed for a minimum of 2 hours.
The 2-hour rest period is vital for depolarization. It allows the internal chemistry to reach equilibrium so the BMS can measure the true open circuit voltage, or OCV.
The OCV acts as the absolute anchor point for the new capacity calculations.
Following this single deep cycle and rest period, The BMS must prove that its freshly calculated capacity estimation coefficient is within plus or minus 2.0% of the true bench-tested capability of the new battery.
If it hits that 2% margin, the DVP&R validation proves the brain and the new heart are perfectly synchronized. The calibration is complete and the vehicle is safe to return to the customer.
The sheer density of testing, tracking, and mathematical filtering required across all 5 dimensions, from the physical chemistry to the manufacturing floor to the highway limp mode response, creates a completely hermetic functional safety ecosystem.
It really is a phenomenal chain of causality. Let's take a step back and look at the massive journey we've just tracked.
It's a lot to take in.
We started by examining the microscopic fracture of carbon structures and the permanent parasitic thickening of the SEI layer.
Then we moved to the abstract mathematical filtering of the dual time scale observer and the DQDV calculus required to peer through the noise of ampere-hour drift.
We toured a heavy industrial factory using beta radiation to guarantee perfectly balanced lithium parking lots down to the microgram.
And we concluded in a thermal shock chamber, validating a 2-second software reaction to a catastrophic failure at 70 miles per hour.
It represents a staggering synthesis of material science, statistical manufacturing control, and real-time computational mathematics. The engineering intent isn't just to make the battery last, it's to ensure that when it inevitably fails, it fails elegantly, predictably, and with absolute safety prioritized above all other metrics.
The processing power dedicated purely to functional safety in these architectures rivals the primary flight computers in commercial aircraft. It is an extraordinary unseen effort.
So the core takeaway here for you listening, the next time you plug your EV into a charger, or the next time you see a diagnostic warning light illuminate on the dash, recognize that it is not just a simple switch being flipped.
There is an invisible, hyper-complex symphony of chemistry, software, and physical engineering working tirelessly underneath the chassis.
The vehicle is literally running aerospace fatigue modeling and high-frequency calculus in your garage while you sleep, actively managing the decay of a volatile organism to maximize its lifespan and keep you safe.
It's incredible when you really think about it.
Which leads to a final provocative thought. We have spent this entire deep dive mapping the immense computational load required to manage and diagnose the degradation of the entire battery pack as a macroscopic whole.
Right. The rain flow matrices, the beta ray scanning, the DQDV curves.
All of it is designed just to figure out that the overall barrel is rotting.
And the macro level diagnosis is computationally heavy enough on its own.
So consider this. If it requires this level of systemic cross-dimensional engineering just to diagnose the macro-level failure of the whole pack.
Oh, wow.
Imagine how impossibly intricate the diagnostic logic must be to hunt down, isolate, and diagnose just one single microscopic weak cell hiding among thousands of completely healthy ones.
Pinpointing a single microscopic anomaly within thousands of interconnected cells is a diagnostic labyrinth that pushes modern computing to its absolute limits.
Something to mull over the next time you hit the highway.